A Brief History of Time by Stephen Hawking. Picture this. A famous scientist, possibly the philosopher Bertrand Russell, is giving a lecture about how Earth orbits the Sun and how our Sun circles around the center of our galaxy. Pretty standard stuff, right? But then, from the back of the room, a little old lady stands up and says, "That's complete nonsense. Everyone knows the world is actually a flat plate balanced on the back of a giant tortoise." The scientist smiles politely, a bit smugly even, and asks, "Well then, what's holding up the tortoise?" Without missing a beat, the old lady replies, "Nice try, young man, but it's turtles all the way down." Now, we might chuckle at this image of an endless tower of turtles, but here's the thing, it actually raises something pretty fascinating. Why are we so sure we know better? What do we really understand about the universe, and how can we be certain? These are exactly the kinds of head-scratchers that drove Stephen Hawking, one of history's most brilliant minds, to write a book that would completely shake up the world. When he published A Brief History of Time in 1988, nobody saw what was coming. Not his publishers, not his agent, definitely not Hawking himself. This book, packed with wild concepts about black holes, the beginning of time, and the fundamental nature of reality, went on to sell over 10 million copies worldwide. It was translated into 40 languages and camped out on the London Sunday Times bestseller list for an absolutely mind-blowing 237 weeks. That's longer than any other book in history. As one of Hawking's friends jokingly put it, he sold more books on physics than Madonna sold on sex. So what made this book catch fire? Sure, the ideas were incredible, but it was really about the man behind them. Stephen Hawking was diagnosed with ALS at just 21 years old and given only a few years to live. But he didn't just survive. He went on to become the most brilliant theoretical physicist since Einstein, doing all his groundbreaking work from a wheelchair and speaking through a computer. His life was living proof that the human mind can break through any physical barrier and literally reach for the stars. Today, we're going to dive into the remarkable ideas packed into this book. We'll explore the biggest questions imaginable. Where did we come from? Why does the universe look the way it does? Did it have a beginning? Will it have an end? And I promise you this, after we're done, you'll look up at the night sky and see it in a completely different way. Our cosmic story doesn't start in some distant galaxy. It begins right here on Earth with our ancestors. For thousands of years, humans believed we were the center of absolutely everything. The Greek philosopher Aristotle, brilliant for his time, was totally convinced that Earth stood still while the sun, moon, and planets danced in perfect circles around us. It was a comforting thought that put humanity right at the heart of creation. Another Greek thinker, Ptolemy, refined this into a complete model of the universe. Earth sat at the center, wrapped by 8 celestial spheres carrying all the heavenly bodies. It was elegant, ordered, and had one huge bonus. It left plenty of room outside the outermost sphere for heaven and hell. The Christian Church embraced this model, and for over 1,000 years, it was considered absolute truth. But here's the thing about scientific truth. It's always waiting for someone brave enough to question it. That brave soul showed up in 1514, a Polish priest named Nicholas Copernicus. He proposed something simpler and more elegant. What if the sun was actually at the center, with Earth and the other planets circling around it? At first, he shared his model anonymously, probably worried about being labeled a heretic. For nearly a century, most people ignored his idea. Then 2 game-changers entered the scene, German astronomer Johannes Kepler and Italian scientist Galileo Galilei. They started publicly backing Copernicus's theory. Kepler refined it, showing that planets didn't move in perfect circles, but in elongated ones called ellipses. Suddenly, the math actually matched what people observed in the sky. The final blow to the old view came in 1609. Galileo, using this new invention called the telescope, pointed it at Jupiter. What he saw shouldn't have been possible according to the old model. He discovered several small moons orbiting Jupiter. This was revolutionary because it meant not everything had to orbit Earth. The old model with its perfect spheres and Earth-centered universe, was shattered. This set the stage for perhaps the greatest scientific mind of that era, Sir Isaac Newton. In 1687, he published what might be the most important single work ever written in physical sciences. In it, he laid out his laws of motion and, crucially, his law of universal gravitation. Newton's idea was breathtakingly elegant. Every object in the universe pulls on every other object with a force that depends on their mass and how far apart they are. The same force that makes an apple fall from a tree keeps the moon orbiting Earth and Earth orbiting the sun. For the first time ever, the heavens and Earth were united under one set of rational, discoverable laws. The universe wasn't a playground for divine whims anymore. It was a magnificent cosmic machine. But Newton's gravity-governed universe created a serious puzzle. If gravity always pulls things together, why didn't all the stars just collapse into one massive clump? Newton thought about this, and figured that if the universe was infinite, with stars spread evenly throughout, there'd be no central point for them to fall toward. Every star would be pulled equally in all directions. It was clever reasoning, but wrong. Even in an infinite universe, a static collection of stars is fundamentally unstable and would eventually start collapsing. For nearly 200 years, this problem got swept under the rug. The belief in a static, unchanging universe was so deeply rooted that it persisted well into the early 20th century. Even Albert Einstein, when he created his revolutionary general theory of relativity in 1915, was so convinced the universe had to be static that he added what he later called his biggest blunder, a cosmological constant to his equations to counteract gravity and prevent universal collapse. Only one person seemed willing to take general relativity at face value. A Russian physicist named Alexander Friedmann used Einstein's own equations to show that the universe shouldn't be static at all. In fact, he predicted it must be expanding. This was in 1922, years before anyone had observed anything to support it. But his work, like Copernicus's centuries before, remained largely unknown in the West. The proof arrived in 1929, courtesy of American astronomer Edwin Hubble. He spent years cataloging distant galaxies and measuring their light. What he discovered sparked one of the greatest intellectual revolutions of the 20th century. When we look at light from a star or galaxy, we can analyze its spectrum, the rainbow of colors that compose it. Astronomers in the 1920s noticed something weird about light from distant galaxies. The characteristic color patterns were all shifted toward the red end of the spectrum. This red shift happens because of something called the Doppler effect. You experience the Doppler effect all the time. When an ambulance races toward you, its siren sounds high-pitched. As it passes and speeds away, the pitch drops. Light works the same way. If a galaxy is moving away from us, its light waves get stretched out, making them appear redder. If it's coming toward us, they appear bluer. Hubble expected to find roughly equal numbers of red-shifted and blue-shifted galaxies, assuming they moved around randomly. But he was shocked to discover that nearly all galaxies were red-shifted. Almost everything was moving away from us. And here's the kicker. The farther away a galaxy was, the faster it was racing away. The only explanation was that the entire universe was expanding. The distance between every galaxy was constantly growing. Think of it like a balloon with dots painted on it. As you inflate the balloon, the distance between any two dots increases, and the farther apart the dots are, the faster they move away from each other. But here's what's cool. There's no single dot that's the center of the expansion. Similarly, the universe is expanding, but it doesn't have a center. Every galaxy is moving away from every other galaxy. This discovery changed everything. If the universe is expanding now, then in the past, everything must have been closer together. Run the clock backward far enough, and there must have been a moment when everything in the universe was squeezed into a single, infinitesimally tiny point. A point of infinite density and infinite temperature. This moment is what we call the Big Bang. The discovery of the Big Bang brought the question of the universe's beginning into the realm of science for the first time. Before, it was purely philosophy, or theology. Now it was a scientific prediction. At that initial moment, all known laws of science would break down completely. The very concepts of space and time would lose all meaning. You could say that time itself began at the Big Bang. Not everyone welcomed this idea. The notion of a beginning felt too much like divine intervention for some scientists. Comfort. They tried finding ways around it. The most popular alternative was the steady-state theory, which suggested that as galaxies drifted apart, new matter continuously popped into existence in the gaps, so the universe would look essentially the same at all times. But the evidence for the Big Bang kept piling up. In 1965, two American physicists, Arno Penzias and Robert Wilson, were working with an incredibly sensitive microwave detector. They kept picking up a faint, persistent hiss coming from every direction in the sky, day and night. They checked everything, even cleaned bird droppings out of their antenna, but the noise wouldn't disappear. Meanwhile, physicists at nearby Princeton University were working on a prediction made years earlier. If the universe began in an incredibly hot, dense state, the glow from that blazing beginning should still be detectable today. But because the universe has expanded so dramatically, that light would be massively redshifted all the way down to the microwave part of the spectrum. Penzias and Wilson had accidentally stumbled upon the afterglow of creation itself, the cosmic microwave background radiation. It was the final nail in the coffin for steady-state theory, and a stunning confirmation of the Big Bang model. So the universe had a beginning. But this beginning was a singularity, a point where our theories completely fail. General relativity essentially predicts its own breakdown. This told physicists that to understand the very beginning, they needed something more. They needed to merge the theory of the very large, general relativity, with the theory of the very small, quantum mechanics. And this is where our story takes another, wonderfully strange turn. At the dawn of the 20th century, science operated on a deterministic view of the universe, championed by French scientist Laplace. He suggested that if we knew the position and speed of every particle in the universe at one moment, scientific laws would let us predict everything that would ever happen. The universe was like a giant clock, wound up and ticking away. But this clockwork dream started crumbling. Scientists realized that a hot object, like a star, should theoretically radiate energy at an infinite rate, which was obviously absurd. In 1900, German scientist Max Planck proposed a radical fix. He suggested that energy couldn't flow continuously, but only in discrete packets he called, quote, quanta. This quantum hypothesis birthed an entirely new physics. But its full implications weren't grasped until 1926, when another German scientist, Werner Heisenberg, formulated his famous uncertainty principle. Heisenberg realized there's a fundamental limit to what we can know about the universe. To measure a particle's position, you have to shine light on it. But the light itself, arriving as a quantum, will disturb the particle and change its velocity in an unpredictable way. The more precisely you try to measure position, the more you mess up the speed measurement, and vice versa. You can know a particle's position really well, or its velocity, but you can never know both perfectly at the same time. The uncertainty in position times the uncertainty in velocity can never be smaller than a certain fundamental quantity called Planck's constant. This wasn't just about imperfect instruments. It was a fundamental, unavoidable feature of reality itself. The uncertainty principle signaled the death of Laplace's deterministic dream. You can't predict the future with perfect accuracy if you can't even measure the present state of the universe precisely. Quantum mechanics introduces an unavoidable element of randomness into science. It doesn't predict one definite outcome for an observation. Instead, it predicts several different possible outcomes and tells us how likely each one is. Einstein, despite helping develop quantum theory, famously objected to this. God does not play dice, he insisted. But experiment after experiment confirmed that quantum mechanics was right. It governs how transistors and computers work, and forms the foundation of modern chemistry and biology. One of quantum mechanics' most mind-bending consequences is wave-particle duality. Particles like electrons can also behave like waves. They don't have one definite position but are smeared out with certain probabilities. This leads to a bizarre phenomenon called interference. Imagine a screen with two narrow slits cut in it. Shine light through the slits, and you get a pattern of light and dark bands on a wall behind it. This happens because light waves passing through each slit interfere with each other, sometimes amplifying, sometimes canceling each other out. Makes sense for waves. But here's where it gets weird. If you fire electrons one by one at the two slits, you get the exact same interference pattern. It's as if each individual electron passes through both slits simultaneously, interfering with itself before hitting the screen. This single experiment captures the fundamental mystery of the quantum world. So now we have two towering theories. General relativity describes gravity and the large-scale structure of the universe, stars, galaxies, cosmic expansion. And quantum mechanics describes the three other forces of nature, the strong nuclear force, weak nuclear force, and electromagnetism, on the tiniest scales. The problem? These two theories are fundamentally inconsistent with each other. They can't both be correct, as currently formulated. General relativity is a classical theory that doesn't incorporate the uncertainty principle. When you try combining them, you get ridiculous infinities. The quest to unite these two pillars of modern physics into a single quantum theory of gravity became the holy grail of theoretical physics and the central focus of Stephen Hawking's life work. And the place where these two theories must meet, where gravity is incredibly strong and scales are incredibly small, is inside a black hole. The concept of a black hole goes back over 200 years. A Cambridge scholar named John Michell figured that a star sufficiently massive and compact would have such powerful gravity that even light couldn't escape. It would be a black void in space. But only with Einstein's general relativity could we truly understand what happens. A star shines by burning nuclear fuel, creating outward pressure that balances gravity's inward pull. Eventually, though, the fuel runs out. For a small star like our Sun, it will cool and shrink into a dense object called a white dwarf, held up against further collapse by quantum forces between its electrons. But what about a much more massive star? In 1928, a young Indian student named Subramanian Chandrasekhar was sailing to England when he calculated that there's a limit to how massive a star can be and still support itself as a white dwarf. If a star's core exceeds about 1.5 times our Sun's mass, now called the Chandrasekhar limit, electron repulsion isn't enough to stop collapse. Gravity wins. The star collapses catastrophically. Its gravitational field becomes so intense that it warps space-time around it. Light rays near the star bend inward. As the star keeps shrinking, it reaches a critical point where gravity at the surface becomes so intense that light can't escape at all. This point of no return is the event horizon. Anything crossing it, light, matter, an unlucky astronaut, is trapped forever, pulled inexorably toward the center, where the star is crushed into a singularity, a point of infinite density where time itself ends. To an outside observer, things look very different. Watching a star collapse, its light appears increasingly red and dim. Time on the star's surface seems to slow down. The final moments just before the event horizon forms appear, stretched out over infinite time. The star fades away, leaving only perfect blackness in space, its immense gravity still warping the cosmos around it. For a long time, people believed the singularity inside a black hole was decently hidden by the event horizon. But the singularity itself remained problematic, a place where our theories failed, a realm of infinite unpredictability. This is where Stephen Hawking made his most stunning contribution. In 1974, he started thinking about how quantum mechanics, specifically the uncertainty principle, would affect space just outside a black hole's event horizon. What he discovered was revolutionary. Black holes aren't completely black. They should glow faintly, emitting a steady stream of particles and radiation. This is now called Hawking radiation. How's this possible if nothing can escape? The answer lies in the quantum weirdness of empty space. According to the uncertainty principle, empty space isn't truly empty. It's a bubbling stew of virtual particles and antiparticles that pop into existence as pairs, separate briefly, then come back together and annihilate each other in incredibly short time spans. Now imagine this happening right at a black hole's event horizon. It's possible for one member of the pair, say the antiparticle, to fall into the black hole while the other, the particle, escapes. To a distant observer, it looks like the black hole just emitted a particle. The particle that fell in had negative energy relative to the escaping particle, so when it enters the black hole, it reduces the black hole's total mass and energy. The result? The black hole slowly loses mass, shrinks, and radiates energy. The smaller it gets, the hotter it becomes, and the faster it radiates. Eventually, after an unimaginably long time for a solar mass black hole, it would completely evaporate in a final tremendous burst. This idea was the first prediction that required both general relativity and quantum mechanics working together. It suggested that gravitational collapse wasn't as final as previously thought. It hinted that quantum mechanics might smooth out the singularities that classical relativity predicted. This led Hawking to the ultimate question: could a quantum theory of gravity do the same for the Big Bang singularity? Could it eliminate the need for a beginning of time? This brought him to his most profound and perhaps most speculative idea, the no-boundary proposal. To grasp this, we need one more strange concept: imaginary time. This isn't science fiction. It's a well-defined mathematical idea. Think of regular numbers on a horizontal line. Imaginary numbers exist on a vertical line, at right angles to the real ones. Hawking proposed that to understand the quantum state of the universe, we need to perform calculations using imaginary time. In imaginary time, the distinction between time and space disappears. Space-time becomes four-dimensional space, like Earth's two-dimensional surface, but with two extra dimensions. Now, Earth's surface is finite in size but has no boundary or edge. If you sail off in one direction, you don't fall off. You eventually circle back to where you started. Hawking and colleague Jim Hartle suggested the universe might work like that. In imaginary time, space-time could be finite, but with no boundary, no edge, and no singularity. It would be completely self-contained. What would this mean for the real universe we experience? The universe would still appear to have a beginning in real time, the Big Bang. It would expand from an incredibly small, smooth, and ordered state, go through a period of rapid inflationary expansion, smoothing out any initial wrinkles, and evolve into the universe we see today. Tiny quantum fluctuations at the very beginning would be amplified by expansion, becoming seeds for galaxies, stars, and ultimately us. In this picture, there's no initial singularity where science breaks down. The beginning of the universe is a smooth, regular point in space-time, like Earth's North Pole. You can't go north of the North Pole, but there's no boundary there. It's just another point. So if the universe has no boundary, no beginning, no end, what place is there for a creator? Hawking famously wrote, "The boundary condition of the universe is that it has no boundary." The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. This doesn't disprove God's existence, but it suggests there may be no role for God in setting the universe in motion. The universe, according to this idea, could have brought itself into existence according to physics alone. This leads to the final great quest: the unification of physics, the search for a single theory describing everything, a theory of everything. For years, the best candidates seemed to be theories called supergravity, but they hit mathematical roadblocks. Then in the 1980s, a new idea took center stage: string theory. String theory proposes that nature's fundamental building blocks aren't point-like particles, but tiny vibrating loops of string. What we perceive as different particles, electrons, quarks, photons, are just different vibrations of these strings, like different notes on a violin string. One of string theory's most remarkable features is that it naturally includes gravity. One vibrational mode corresponds to the graviton, the particle carrying gravitational force. For the first time, physicists had a theory seemingly capable of unifying gravity and quantum mechanics. But string theory comes with strange predictions. It appears consistent only if spacetime has more than the 3 space dimensions and 1 time dimension we're familiar with, usually 10 or 11 total dimensions. Where are these extra dimensions? The idea is they're curled up into a tiny, compact space, so small we never notice them. This leaves us at the frontier of modern physics. We have partial theories that work incredibly well, but we're still chasing that single, elegant, unified theory. Will we find it? Hawking was cautiously optimistic, believing we might discover it within the lifetime of some alive today. If we do, it would be the ultimate triumph of human reason. It would let us understand the laws governing our existence. It would allow us, in his famous words, to know the mind of God. So what do we take from this incredible journey through space and time? For me, the most powerful lesson in A Brief History of Time isn't just about physics. It's about the relentless, unstoppable power of human curiosity. It's a story about our deep need to make sense of the world, to ask why, and to refuse accepting just because as an answer. Hawking takes us from ancient Greeks seeing gods in the sky, to Newton seeing cosmic clockwork, to Einstein seeing a dynamic curved fabric of reality, and finally to the quantum world, where reality itself shimmers with uncertainty and possibility. It's a beautiful reminder that our understanding of the universe isn't static truth, but an evolving story, and we're living in one of its most exciting chapters. The book also teaches us something profound about our place in the cosmos. In one sense, we're completely insignificant. We live on a tiny planet, orbiting an average star in the suburbs of one galaxy, among hundreds of billions. Yet through the power of our minds, we can reach out and comprehend the entire universe, its beginning, its laws, its possible fate. As Hawking himself embodied, our minds are the true marvels of this universe. How can we apply these grand ideas to our own lives? Here are a few thoughts. First, next time you have a clear night, go outside and just look up at the stars. Don't just see them as pretty lights. See them for what they are. Giant nuclear furnaces, thousands of light years away. Realize the light hitting your eyes began its journey long before you were born, in some cases, before human civilization began. Let yourself feel the awe and wonder of that scale. It's humbling and deeply enriching, connecting you to the grand cosmic story. Second, embrace uncertainty. The uncertainty principle isn't just a rule for subatomic particles. It's a beautiful metaphor for life. We can't know everything. We can't predict the future perfectly. And that's not a failure. It's a feature. It's what allows freedom, surprise, and growth. Instead of fearing the unknown, we can learn to see it as a space of infinite possibility. Finally, never stop asking questions. The entire history of science is a story of people unsatisfied with the answers they were given. They asked, what if? What if Earth isn't the center? What if time isn't absolute? What if black holes aren't black? These questions move humanity forward. In your own life, cultivate that same curiosity. Question your own assumptions. Stay open to new ideas, even when they seem strange or counterintuitive. That's the spirit of Stephen Hawking, and it's the spirit of all great discovery. That was the book summary of A Brief History of Time by Stephen Hawking. We've covered the highlights today, but I'll be honest, a summary can only take you so far. The real magic happens when you read the book yourself. It's in those quiet moments when a particular story or simple phrase hits you unexpectedly. This summary is designed to help you decide if this book is worth your time. If anything we've discussed today resonated with you, grab a copy, because reading it isn't just learning, it's an experience that can genuinely change how you see yourself and your daily life. Also, if you found this summary valuable, please subscribe to the channel so you don't miss our next journey into another life-changing book in the billionaire's bookshelf. Let's keep growing together.